Hi everyone, my name is Woojin Kim from the IDAS lab at Seoul National University. Thank you for joining the presentation. Today, I'll be introducing a recent paper from Anthropic titled Persona Vectors, Monitoring and Controlling Character Traits in Language Models. It was released earlier this year. This paper investigates how large language models exhibit stable personality-like traits and how these traits can be systemically extracted, steered, and even monitored during the training process. The notion of activation-based steering itself is not entirely new. Some previous work has already shown that internal activations in language models can encode conceptual directions. However, this paper goes further. It demonstrates that persona vectors can track how traits shift during the fine-tuning process and even predict whether a training sample will push the model toward undesirable behaviors. These aspects, some of like behavior drift tracking and dataset filtering using internal representations, offer novel insights into model alignment and safety. In the next few slides, I'll walk through how persona vectors are constructed, how they're used for steering, and how they can help ensure safer, more interpretable model training. Here is the outline for today's presentation. I'll start with a brief background on LLM personas, what we mean by persona, how personality traits appear in language models, and why this matters. Then I'll move on to activation engineering, which is the broader family of methods that modify a model's internal activations. This sets up the motivation for persona vectors. After that, I'll walk through the main contributions of the paper. First, how persona vectors are constructed and used for steering. Then, how they can be used for monitoring behavior shift during the training process. Next, how they can also be used for preventing unwanted trait drift. And finally, how persona vectors can help filter data sets by predicting their potential to induce harmful traits. First, let's start with the notion of personas in large language models. Large language models today often behave as if they have personas, like consistent styles, preferences, or behavior tendencies that are not explicitly programmed. These personas emerge naturally from pre-training on large-scale human text. Recent work on role-playing language agents, or RPLA, shows that instructing an LLM to adopt a persona results in highly structured and consistent behavior patterns. This points to a deeper question: do LLMs actually internalize latent traits? First, let me briefly introduce what we mean by persona in large language models. In psychology, a persona refers to the outward character or role that a person projects, often different from their private or internal self. In the context of LLMs, we can think of persona as a stable pattern of behavior or style that consistently emerges in generated text. This includes things like personality traits, preferences, politeness level, optimism, or even sycophancy. To understand this more concretely, we can categorize LM personas into three types. First, the demographic personas. This reflect the broad groups of people, such as doctors, chefs, students, or introverts. Models often acquire this pattern simply from large-scale pre-trained data like Common Crawl. When you prompt a model with act as a doctor or act as an introvert, the model tends to respond in a way that matches these demographic stereotypes. The next is the character personas. This involve well-established fictional or historical figures, like Harry Potter, Napoleon, or Aristotle. The model learns these personas from Wikipedia, novels, or something like movies. When model is prompted, it can imitate their tone, opinions, or decision-making style. And finally, the individualized personas. These are more dynamic and personalized profiles. For example, travel agents, writing assistants, or a personal secretary that adapts to your preferences over time. These personas emerge through interaction histories or personalized data and are commonly used in chatbots or long-term assistants. Across all these types, the important idea is that LLMs do express consistent behavior patterns, almost like personality traits. Another way to understand persona in LLMs is through personality traits and the behaviors they induce. Many works evaluate models using psychological frameworks like the ocean traits. In these traits, models respond to personality inventory questions, and the resulting scores map onto characteristic behaviors. For example, high openness correlates with imaginative or creative responses, while high conscientiousness produces more structured and careful explanations. What's important here is that these traits appear consistently across different prompts, suggesting that LLMs contain stable internal directions that encode these tendencies. Shows another perspective on persona-like behavior in LLMs. Beyond the big five traits, researchers have also evaluated models on well-known personality taxonomy such as the MBTI types. What's interesting is that different language models consistently map to different MBTI profiles. For example, ChatGPT often shows patterns similar to ENTJ, while GPT-4 tends to toward INTJ, and other open source models cluster around types like ISTJ or INFJ. These MBTI tendencies are derived from the model's answers to large sets of psychological assessment questions. And although these tests were originally designed for humans, LMs exhibit surprisingly stable patterns across runs. So, the main point of this slide is that persona-like traits emerge naturally from the model's internal representation, even when we don't explicitly ask the model to adopt a persona. The most widely discussed behavior traits in LMs today are the 3H principles and sycophancy. The 3H stands for helpness, honesty, and harmlessness. These are the core alignment goals we expect modern LMs to follow. For example, giving correct information, avoiding harmful content, and being generally cooperative. On the other hand, one problematic trait that frequently emerges is sycophancy. This is when the model tries too hard to agree with the user, even when the user is wrong. You can see an example on the right. The user gives an incorrect answer and the model simply agrees with it. So these two sides, alignment principles like 3H and undesirable behaviors like sycophancy, represent the kinds of personality traits we observe in current LLMs. Steering a language model toward a specific persona can be done through many different approaches. For example, you can modify the prompts, you can fine-tune the model, you can apply path methods like LoRa, or even use reinforcement learning to nudge the model toward certain behaviors. But today, I want to highlight the activation-based steering, which is the focus of the paper. As shown in the middle panel here, the general workflow is you initially take a data set that expresses a concept, then we extract hidden states across layers, then compute a direction that distinguishes positive versus negative examples, and then inject that vector back into selected layers to shift the model's behavior. Next, before diving into persona vectors, I'll briefly introduce the basics of activation engineering, which is the core mechanism behind this paper's steering method. Large language models are built from many components: attention heads, feed-forward networks, and layer norms, and each part encodes different kinds of information. The feed-forward layers tend to store factual or conceptual features, while the key-value pairs in attention capture relationships between the tokens. Normally, when we fine-tune a model, we end up reshaping these internal representations, which essentially rewrites the model's long-term memory. Fine-tuning modifies these internal representations, essentially rewriting the model's long-term memory. But because models today have billions of parameters, fully training them has become extremely expensive. So, the activation engineering takes a different approach. Instead of rewriting the entire model memory, it focuses on modifying the model's current internal activations, its moment-to-moment thought process. By identifying how a concept, like love in this example, is represented inside the model, we can then inject that representation back into the model to steer its behavior in real time. This idea, controlling the model by editing its activations rather than its parameters, is what we refer to as activation engineering or representation engineering. Then, in this slide, I will explain what an activation actually is inside a language model. In an LLM, every layer produces a numerical representation, a vector or tensor, as it processes the input. This is essentially the intermediate output of each layer. If we write it formally, the activation at layer L is just a layer's transformation applied to the previous hidden state. But conceptually, you can think of an activation as the model's momentary thought process at that point in the network. The key idea behind activation engineering is that if we modify these activations, even slightly, we can directly steer the model's behavior. The diagram on the right shows this. We inject the concept vector at a specific layer, and the downstream layers propagate the change, ultimately producing a steered behavior. This slide illustrates the core workflow behind contrastive activation engineering. On the left, we first compute the steering vector by passing two contrastive sets of inputs through the model, typically a positive set and a negative set that differ along a specific concept or trait. Then we extract the hidden states at the chosen layer, usually at the final token, and take the difference between the positive and negative averages. This difference becomes our concept or steering vector. Then, on the right side, during the generation process, we simply inject this vector back into the model's residual stream at the same layer. By scaling the vector with some coefficient and adding it at each generation step, we can continuously steer the model's behavior in the desired direction. These are some representative related works on activation-based behavior steering. On the left, ACTED from 2023 takes a very simple approach. It uses a single pair of contrasting prompts, like I love talking about weddings versus I hate talking about weddings. Then computes the difference between their activations and uses that as a steering vector. This vector is then injected during generation to shift the model's behavior. Then the right side, the CAA extends this idea by using many contrastive examples. Instead of depending on a single prompt pair, it aggregates activation differences across multiple behavior eliciting pairs, giving a more robust and general steering direction. Both methods have additional details around where to inject and how strongly to inject the vector, but for our purposes today, I'll just focus on this basic idea. First, find contrastive activations, then compute the direction, then edit during inference to steer the behavior. So activation-based method used for attacks or safety alignment. On the left is TA2, the Trojan activation attack. The idea is that an attacker can craft malicious steering vectors and inject them into a clean model's activations. These vectors are then quietly embedded into the model, and once deployed, the model produces misaligned or harmful outputs even though the base weights are never modified. So activation steering can be abused in a similar way to a Trojan. On the right is CAST, which uses activation steering for the opposite purpose, to improve the safety. Instead of blocking everything, CAST introduces conditional repressor vectors that selectively trigger the refusal only for harmful prompts, while still answering the harmless ones normally. So, this highlights both sides of activation engineering. It can be exploited for attacks, but it can also be used to build more precise and controllable safety mechanisms. Besides behavior steering, activation-based methods are now also being used to improve the in-context learning itself. For example, iterative vectors and in-context vectors extract latent directions from a set of demonstrations, and then apply those directions directly at inference time. The nice part is that once these activations are computed, we don't need to repeatedly supply long demonstration prompts. Instead, we can cache the activation that a long prompt would have produced, and inject it directly during the inference. This lets the model behave as if it had been given the full prompt, while making generation much faster and more efficient. There are also a few other directions within activation engineering that are worth briefly mentioning. First, on the left, we have BIPO. This method learns a steering vector through a reinforcement learning style objective using preference pairs. Compared to simple contrastive methods, BIPO tries to directly optimize the steering direction so that it aligns with human-defined real-world differences. So rather than just subtracting activations, it actually learns the best direction by iteratively updating it with a real-world model. On the right, we have ACT, the activation transport. This line of work frames steering as an optimal transport problem. Instead of simply adding a vector, ACT transports the model hidden states from a source behavior to a target behavior in a more geometrically precise way. This often produces smoother, more controlled transformations than traditional vector addition. Now, let's move on to the main part of today's talk and look at how personal vectors are constructed and used for steering model behavior. The mechanism for extracting persona vectors is actually very similar to the activation-based method we saw earlier. We start by constructing contrastive pairs, in this example, an evil persona versus a helpful persona. For each side, we prompt the model to role-play the trait, generate a batch of responses, and then extract the hidden activations from those responses. We then average the activations from the trait expressing responses. Then subtract the average activation from the non-trait responses, and the difference becomes the persona vector for the trait. So essentially, a persona vector is just a contrastive activation direction that captures how the model internally represents a specific character trait. Like evil or sycophantic, the first step is to automatically generate trait-specific artifacts. This includes creating a small set of positive instructions that encourage the trait and negative instructions that explicitly discourage it. In the paper, they construct 5 positive-negative instruction pairs for each trait. They also generate about 40 evaluation questions that are designed to reliably evoke that trait in the model's behavior. And finally, they create an evaluation prompt that will later be used by a judge model to score the generated responses. Once we have the trait-specific questions and prompts, the second step is to actually extract the persona vectors. For each evaluation question, we generate 2 responses, one using the positive instruction set and one using the negative instruction set. Then we score these responses with a judge model and filter out only the strongly trait-relevant ones. For every remaining response, we collect the residual stream activations at every layer and average them across the tokens. Finally, we compute the persona vector simply as the difference between the positive and negative activations. This gives us a clean, direction-like representation of each trait. For example, evil, sycophantic, optimistic, apathetic, humorous, and so on. Now that we've extracted persona vectors, the next step is actually steering the model with them. Given a persona vector V, we simply inject it into the residual stream at a particular layer by modifying the activation to H prime, which is the original H plus some coefficient times this persona vector. The plots here show how different steering strengths affect trait expression across the layers. What we constantly see is the middle layers, around layers 12 to 20, tend to be the most responsive. Injecting too early or too late has much bigger impact. At the bottom, you can see examples of how the model's responses actually change. When we steer toward evil, the assistant becomes malicious. When we steer toward sycophancy, it becomes excessively agreeing. And when we steer toward hallucination, it confidently fabricates the details. So, in overall, these persona vectors give us fine-grained and layer-wise control over the model's behavior, and the steering effect is both strong and interpretable. Now that we've covered the steering, let's move on to the second contribution of the paper, using persona vectors as a tool for monitoring internal model traits. With the persona vectors, the now question is, can we actually use these vectors to monitor a model's behavior before it even generates a response? The idea is quite simple. For a given prompt, we look at the activation of the final prompt token, the right before the generation starts, and project that onto the persona vector. If the prompt itself pushes the model toward a certain trait, this projection will increase. So, by generating prompts that interpolate between trait suppressing and trait promoting instructions, you can observe how strongly the model is being pushed toward the persona even before any output is produced. This gives us a way to continuously monitor latent traits in the model just from the activations. That the projection of the prompt's final token activation onto each persona vector strongly predicts the model's downstream behavior, meaning the persona vectors are not just steering tools, but reliable early warning indicators of trait expression. So now we've looked at monitoring traits at the prompt level, but the same idea becomes even more powerful during the fine-tuning process. The key idea is that when we fine-tune a model, its internal persona can shift, sometimes subtly, sometimes dramatically. So here, we use persona vectors as diagnostic tools to track how the model's behavior changes over time. To do this, the authors build small datasets that reliably elicit traits like evil, sycophancy, and hallucination, as well as an emergent misalignment dataset such as incorrect medical advice. For each dataset, they take the base model and the fine-tuned model and extract the average hidden state at the last prompt token. The difference between these activations essentially reveals the behavior shift caused by the fine-tuning process. And importantly, this shift aligns strongly with the corresponding persona vectors. So if fine-tuning begins to push the model in an undesirable direction, say increasing sycophancy, you can directly observe it in activation space. Looking at what happens after the fine-tuning. Using the persona vectors, we can quantify how traits like evil, sycophancy, and hallucination shift depending on the dataset used for the fine-tuning. Each bar here measures the projection of the model's hidden states onto the trait vector. So, higher means that model expresses the trait more strongly. What's interesting is that even when a dataset isn't designed to induce a specific trait, some unintended traits still increase. For example, medical data increases hallucination, and code datasets tends to reduce evil but slightly increase hallucination. Overall, this shows that persona vectors let us track both intended and unintended behavior shift across domains, giving us a direct signal of how fine-tuning is reshaping the model's personality. Result of the monitoring approach. Each point here represents a model fine-tuned on a specific dataset. The x-axis shows how much the internal activations shifted along the persona vector during the fine-tuning, and the y-axis shows the actual behavior trait score after fine-tuning. What you can see is a remarkably strong correlation across all traits, evil, sycophancy, and hallucination, and across both QN and llama models. This means when the model's internal activations shift along the persona vector, its external behavior shifts in the same direction. So, persona vectors are not only useful for steering, they also act as a reliable monitor of how fine-tuning changes a model's character traits. Now that we've seen how persona vectors can detect behavior drift, let's move on to how they can also be used to prevent misalignment before it happens. Seeing how persona vectors can detect behavior changes, the natural next question is, can we actually prevent or correct these unwanted shifts? When we fine-tune a model, especially on domain-specific data, we often unintentionally introduce new traits. For example, training on medical mistakes can accidentally increase hallucination or overconfidence. So, the goal here is to undo or avoid those unintended behavior drifts. The paper proposes two intervention strategies. First, the post-hoc intervention. This means after the model is already fine-tuned, we adjust its internal activation using persona vectors. If fine-tuning accidentally pushes the model in the evil direction, we can simply subtract the evil vector from the hidden state during the inference. It's like applying a correction filter on the fly. Then the next is during training intervention. Instead of waiting until the model is already misaligned, we proactively monitor its internal representation as it learns. Whenever we detect the model shifting toward the undesirable trait, we counteract it by injecting the opposite vector during the training. This works like preventative steering, guiding the model away from problematic directions before the behavior appears at inference time. We can use persona vectors to subtract behavior changes from the model's activations. For example, if a safety tuning process accidentally increases sycophancy, we can detect that shift and subtract the sycophancy vector during inference. And this is the very basics of inference time steering results. Then, for during the training intervention, persona vectors act as a real-time diagnostic tool. We can detect if the model is drifting toward harmful traits and incorporate the signal as a constraint during optimization. This is analogous to adding a regularizer toward a desired behavior directions. You can see that this during training intervention is more effective than before post-hoc training intervention. Done with this, we can find a data set that is responsible of injecting those specific behaviors. We focus on monitoring persona shift and correcting them after they occur. Now, we ask a more proactive question. Can we predict which training datasets will cause unwanted persona shift before we fine-tune the model? To do this, the paper introduces a concept called a projection difference. Here's the idea. We start with the training dataset consisting of input-output pairs. For each training example, we compute the model's hidden activation, specifically the last prompt token activation, and project it onto the persona vector. Then, using the base model, we generate its own response to the same input and compute the projection again. The difference between these two projections tells us how much the training example is trying to push the model along the persona direction. By averaging this over the entire dataset, we get one score, the projection difference, which serves as a predictive signal. If this is large, the dataset strongly encourages the persona trait. In other words, it's likely to shift the model in an undesirable direction if we fine-tune on it. This gives us tools to flag harmful datasets before fine-tuning even begins. Does projection difference actually work as a predictor? The results are quite good. Each point on this scatter plot represents a distant fine-tuning dataset. On the x-axis, we have the projection difference computed before the fine-tuning. On the y-axis, we have the actual trait expression measured after fine-tuning. Across all traits, evil, sycophancy, and hallucination, and across both QN and llama models, we see very clear positive correlations. This means that datasets with larger projection difference indeed produce stronger persona shift when used for fine-tuning. The method is therefore not just intuitive, it's predictive. It allows practitioners to estimate how a dataset will influence the model's behavior without running it the expensive fine-tuning time step all over. Validate that projection difference can be used practically to improve the data quality. Here's the setup. They take a large pool of data and sample subsets based on their projection difference scores. So, the high projection difference means that it's likely harmful, and low projection difference means likely safe. Then, they actually fine-tune the model on these subsets. The results are very clear. Without filtering, high projection difference datasets cause significant increases in evil, sycophancy, and hallucination. With element-based filtering, these harmful shifts are dramatically reduced. And importantly, filtering does not harm model quality. Traits remain low while the model stays functional. At the bottom, you can see real example generations. The unfiltered model produces harmful, unsycophantic, or hallucinated responses, while the filtered version stays aligned. So overall, projection difference is not just a theoretical measure, it's a practical tool for proactively filtering out dangerous training data and keeping fine-tuned models aligned. Okay, then this is the end of my presentation, and thank you for listening.